Special relativity, introduced by Albert Einstein in 1905, marked a paradigm shift in our understanding of space and time, especially at speeds approaching the speed of light. This groundbreaking theory is built on two key postulates. The first is the principle of relativity, which states that the laws of physics are identical for all observers in inertial, or non-accelerating, reference frames. Whether an observer is moving at a constant velocity or standing still, the fundamental laws remain the same. The second is the constancy of the speed of light, which asserts that in a vacuum, the speed of light is always the same, approximately 299,792 kilometers per second, or about 186,282 miles per second, regardless of the motion of the light source or the observer. From these principles emerge several fascinating and counterintuitive phenomena that occur at high speeds. One is time dilation, where time slows down for objects in motion relative to a stationary observer. The faster the motion, the more pronounced this effect becomes, especially as speeds approach the speed of light. Another is length contraction, where moving objects appear to shrink in the direction of motion when observed from a stationary frame. A third phenomenon is relativistic mass increase, where an object's apparent mass grows as its speed increases, requiring exponentially more energy to accelerate it further as it approaches the speed of light. One of the most famous outcomes of special relativity is the iconic equation, E equals mc squared. Here, E represents energy, m stands for mass, and c is the speed of light. This equation shows that mass and energy are interchangeable. A small amount of mass can be converted into an enormous amount of energy because the speed of light, c, is such a large number, and it is squared in this formula. This principle explains the immense energy released in nuclear reactions such as fission and fusion, which power stars, nuclear power plants, and even atomic weapons. The Lorentz transformations, developed by Lorentz, provide the mathematical foundation for understanding how measurements of space and time change between observers in different inertial frames. These transformations mathematically capture the effects of time dilation and length contraction. For time dilation, the relationship is expressed as t prime equals t divided by the square root of 1 minus v squared divided by c squared. In this equation, t prime is the time observed in the moving frame, t is the stationary time, v is the relative velocity, and c is the speed of light. This formula shows that as the velocity, v, increases and approaches the speed of light, time in the moving frame slows down relative to the stationary frame. For a length contraction, the relationship is given as L prime equals L times the square root of 1 minus v squared divided by c squared. In this equation, L prime is the contracted length observed in the moving frame, and L is the length in the stationary frame. This formula shows that the faster an object moves, the shorter it appears along the direction of its motion when observed from a stationary frame. Together, these principles and equations redefine our understanding of space, time, and mass at high velocities. They reveal that space and time are not absolute but are interconnected and depend on the observer's motion. In this series, we'll explore these revolutionary ideas, examine their limitations, and introduce an alternative perspective, the space-filling matter hypothesis, which offers fresh insights into the mysteries of the universe.